physical scientists and math and computer scientists. So work heavily in the space of challenging problems, and in particular with complex systems. So I work with this ISC, and we focus on building multidisciplinary teams, often involving physical scientists and engineers and researchers in AI, to just kind of start to see how AI methods can actually help improve some of these disciplines and overcome some of the challenges. So today, what I'm going to do is present our work on climate tipping points. And this work was originally funded through a DARPA program. And the project that we had proposed called Pac-Mans, and I did not use ChatGPT for any of these acronyms, just so you know. Yeah, so we started there. That program ended. And then we were internally funded with basically an IRAD fund from APL to kind of continue that work. What we started with was just building basically a framework for how AI could be used to assist climate modeling for tipping point discovery. And we actually did it quite well. And then we thought, well, now that we had something, we're starting to able to finally ask some interesting questions that related more to the science itself. And some of those questions are what fueled this new work, which is, you know, is this generalizable to more than just one tipping point? We started with the AMOC or Pac-Mans, and so now we're working with other tipping points. And then how do we study the cascading problem? How do we study mitigation, intervention, all of those things? We wanted to build a way to perform those kinds of studies. And that's where we sit today, is working on that kind of research. And it's a big, the initial team was a multidisciplinary team and involved researchers from APL and also Johns Hopkins University, spanning multiple disciplines, including oceanography, environmental science, chemistry, mathematics, and AI. So we have a huge team. And it's actually grown with the new work that we're doing now. We still have the affiliation with Johns Hopkins University, but now since we're kind of exploring some of these other interesting questions, we've added a bunch of subject matter experts to the team. And so I'm going to just ground this talk with formally defining a tipping point. I'm sure most of the people in the audience know this, but I'm just doing that to formalize it a bit. So we define a climate tipping point as an abrupt response to small changes in forcings, where small perturbations can result in major shifts in state. That response tends to be nonlinear and irreversible. And in this graphic is great on the right-hand side. This comes from the Climate Tipping Point report out of Exeter. I've been getting involved with that report. They're starting to try to build this annual report on tipping points now. But that graphic on the right, we see a system that starts in one of two stable states, and then it starts to lose some stability over time, given external forcings. And once tipped, then that system is going to undergo some abrupt change. And so the initial stable state is no longer visible. And then the system enters essentially a new state. So in the context of chaotic dynamical systems, tipping points are defined as in terms of bifurcation theory, and maybe more widely in terms of phase shifts. And a fold bifurcation, which is depicted in this schematic, is a type of bifurcation in a dynamical system where you have two stable attractors, and between them, an unstable region. When forced, that system is going to pass a tipping point and move from one of those stable attractors to another. So because that's abrupt, that's where there's some implications in terms of the effects. And to speak to it more concretely, on the left, we show a diagram of Greenland ice sheets and how through satellite observations, there appears to be this decrease in the Greenland's reflectiveness, which results in an acceleration, or can result in an acceleration of melting. And so reaching some melting threshold is a good example of a tipping point. And then on the right, what I show is a number of tipping points that have been identified by the IPCC in terms of global warming. And so the group in Exeter, they've done a lot of work in this space. They've identified 15 different of these tipping points that are currently active. And so what you're seeing here is in terms of that gradient for each one of these tipping points, you're seeing the as you're increasing that global warming, what's the, you're moving in terms of likelihood of a tip. So in 2022, global warming was about 1.8 degrees Celsius, or above that now. But you can see that when we get to about 2 here, and as there's speculation that we could even see numbers in terms of 3 or 4 degrees warming. We're getting a lot of these that are past the point of very likely tipping. And I think it's important to look at it in terms of global warming, because we are seeing these temperature anomalies. So in this graphic, NOAA reports that the global surface temperature was about 1.32 degrees Celsius above the 20th century average of 13.7 degrees Celsius. And then April 2024 was the warmest April on record for the globe in NOAA's 175-year record. And so you couple that with the fact that you can think of these tipping points as part of an interconnected system. So with one of these tipping, right, you have those feedback loops there, and you're likely to see cascades occurring. So in my mind, it's important to look at it in terms of it being this interconnected system, and also in terms of warming, because you can get these accelerations that maybe aren't even accounted for in some of the plots we see today. All right, so unfortunately, studying climate tipping points, it's very challenging to study them using your typical GCMs for climate projections, because they depend on a number of physical processes that are governed by very poorly constrained parameters. So trying to explore that entire space spanned by those parameters is just computationally infeasible. And that's really why DARPA created that program that was called AI-assisted climate tipping point modeling. And by the way, that program was completely open source. So all of the work that came out of that program is available online. And so they're asking in that program, they were just trying to ask the question, where do we start? How can we use AI to actually try to overcome some of these limitations? And so what did we do for this program? We built this AI-assisted climate modeling methodology. We developed reduced models. So we started to work with these reduced models that represented the larger climate space with high fidelity, meaning it actually could represent, these reduced models still represent the dynamics, but they're coarser, right, than the larger models. And then we built TIP-GAN to discover tipping points in these models. And then we built something called TIP-Assist to actually work as an AI assistant to allow physical scientists to interact and actually use natural language to interact with the system. Of late, we've developed something called TIP-CAUSE to learn what are the strongest drivers of those tipping points. We actually proposed to do that in that DARPA work, but it really is it's a really challenging space, and so we ran out of time. So we started working on that with our latest work. So what I'm going to do is kind of run through some of the work that we've done, and I'm going to talk to this in terms of how it's transpired temporally. So I'll talk to the work that we did in the beginning with DARPA, and then what we're doing now, because what we're doing now, we're really excited about this work. So with the DARPA program, we built this AI approach, and we used the Atlantic Meridional overturning circulation, or the collapse of it, as our tipping point. Our collaborator from Johns Hopkins University, Anand Manidesakan, actually created one of these reduced models of the AMOC to actually study that overturning behavior. And I'm sure everyone is aware of the AMOC, this large climate system related to our ocean currents that's driven by water density differences based on temperature and salinity changes. It was noted in, I believe, a paper that there was a slowing in 2009 and 2010. I know there's like contention there as to whether that what we saw was actually related to a slowing. Saw like extreme sea level rise, some extreme temperatures in Europe, and then more extreme hurricane season in the Atlantic in that time period. And then of late, we've been learning more about the likelihood of a weakening in the 21st century due to an increase in greenhouse gases. And even there's been recent speculation, actually quite a bit of speculation recently, as to the likelihood of a full collapse occurring. And so it's definitely a critical system to study. And it's nice that we had a collaborator who's pretty much spent most of his career in this space. And so, so we can use these reduced models to actually allow us to basically build the data sets that we need to train these tipping point models, the AI models. And so in this 4-box model, essentially it's a very coarse version of the ocean. You have 4 boxes that represent some part of the ocean. You have basically the southern, northern parts, the low latitudes, and then a very large box for the deep part of the ocean. And so the idea here is that we're looking at the mass balance equation and the depth of the low latitude box, and the AMOC is going to be in this one state when that mass is removed, and then the AMOC is basically in an off state when the mass is recycled in that low latitude. And so we can actually look at the result of that overturning parameter in terms of the parameters in this model to be able to determine if the AMOC is in a state where it's on or off. And so we built something called a TIP-GAN, and I'll just give a little bit of a background about generative adversarial networks. It's based on a generative adversarial network. With a generative adversarial network, we have 2 networks that are in this adversarial game. The first network, the discriminator, is going to learn to distinguish between real data samples from a training data set and fake samples from a generator. And then that second network, the generator, or in our case, we have multiple generators, but the second network, the generator, is going to start with random noise, and then it's going to learn how to produce fake samples that resemble the real data. And the discriminator provides some feedback to the generator on how well those generated samples match that real data distribution. And then over time and iteration, what will happen is both networks will prove, and eventually they'll reach some kind of equilibrium. TIP-GAN that we've created based on a GAN, it's a little different. It's built specifically for climate tipping points, and it's using a team of generators. So originally there was a paper that was developed on increasing the number of generators in a GAN to actually improve the stability of the GAN. So we kind of take advantage of that in some way because we have this large space. Even with the reduced models, we use these generators actually to try to explore the different modes of that space. And these generators, what they're doing is they're trying to imagine initial conditions that will result in a tipping point, in this case, the AMOC off. And another key difference about our network is that during training, this discriminator is actually going to call on the reduced model. We call it a surrogate in this picture, but it's the reduced model. So it's actually running the model out in model time to get an answer as to whether the initial conditions will result in a tip or not of the AMOC. What's interesting is that, and this is where the real win comes from this network, is that once it's trained, that discriminator is no longer calling on the reduced model. So you basically have trained your discriminator to be a very highly accurate classifier of whether these initial conditions will result in the AMOC tipping or not. So you don't have, you're saving a lot of time. You're not running that network. And then those generators are very interesting because now you can tell them generate thousands, tens of thousand initial conditions that will result in the AMOC tipping. So it's actually quite powerful. And what's interesting, what came out of this work, is that we were trying to understand how does this GAN learn something about the state space working in parameter space, because that reduced model is running, you know, the discriminator calls on it, it's running out, but the generators don't know anything about what's going on at each time step. All they know is these are the initial conditions and this is what resulted. So it's really learning in parameter space. And so the question is, you know, can the GAN learn something about the state space just by parameter perturbation? And so what we found was that there are certain times when the discriminator is more uncertain about whether a model will tip or not, given the initial conditions. And it appears from the study that we did that the uncertainty roughly aligns with the unstable area in the state space with regards to the fold bifurcation that was present in the reduced model. So we're trying to explore that a bit and see if we can exploit it in some way using the generators. So we imposed something on the loss function where we actually have the generators evaluate in terms of how they're going to do their perturbation, some uncertainty from the discriminator. So it's getting some feedback from the discriminator about how certain it is as to whether a model will tip or not in terms of its prediction. And so we generated this very carefully crafted experiment where we tried to recreate the 2018 experiments that were in our collaborators' paper, who actually authored that 4-box model. And we constrained the experiment to perturbing 3 parameters: thermocline depth of the low latitudes, the Ekman flux from the Southern Ocean, and the freshwater flux in the north. And so each generator essentially had 2 objectives here, right? Guide the discriminator into predicting that the initial conditions are sampled from the real distribution. That's like your typical GAN thing. And then also generate model initial conditions where the discriminator is least certain about its output state. So slightly different than trying to just generate initial conditions that will result in tips. Now, these generators are focused on generating conditions that will present cases where the discriminator is the most uncertain. And it turns out when you set that problem up, that TIP-GAN up in this way, it does a pretty good job at modeling that fold bifurcation. So what you're seeing here is, this is from the paper, and you're seeing experiments in terms of changing the Ekman flux as a function of the freshwater flux, what's the overturning values. And so anything 0 and below means we're in an off state, anything above means we're in on state. And you can see we see this fold bifurcation occurring in these simulated runs. We can recreate that with our generators. So this is a test data set that we held out, and this is with 1 generator. Now, because of the way we set up the objective function, as we increase the number of generators, it turns out that generators get very focused on just that area where we have the most instability. So the 2 red parallel lines you're seeing are basically thresholding where you have the most instability in terms of the fold bifurcation. And so, so this was a very interesting result that came from our work. It showed that, you know, the GAN in parameter space was learning something about that bifurcation that's occurring in state space. And consistent with that was that the discriminator F measure results in terms of predicting whether models would tip or not once it was trained was reduced as you increase the number of generators, because the generators are trying to push it into that area where it's most uncertain. And so we were able, with this TIP-GAN, we were able to show parameter regimes that were previously less explored by the physical scientists, which was a nice finding that came out of it. Ideally, we would want this TIP-GAN to make new discoveries. That's what we're after. One thing that came out of this early work was that the TIP-GAN was actually able to discover recoveries. So the AMOC would collapse and actually recover from the collapse. And that was something that was previously they weren't expecting that from this box model. So that was something interesting that came out of the work. We decided from this work that increasing the number of boxes, so increasing the number of parameters, would make this a little more interesting in terms of a study, and that's what we've done since then. So before I talk to that, though, I want to talk about the early work that we did with the AI assistant, particularly because I know this group, you know, Michael and I have had discussions around LLMs and the work that your group's been doing, and I think there's some interesting relationships between what we've been doing, what's being done at NASA. And so ideally what we wanted to do was build a interface that allowed physical scientists to interact with the AI models without knowing anything about AI. So provide an interface where they could pose natural language questions, and we would translate those questions into a representation that our AI models could interpret. So this is really before ChatGPT just took off. This was actually prior to that. So we were using multiple encoder decoder architectures, and so we were creating this bi-directional translation. So what we were trying to do ultimately was move from natural language to neurosymbolic representations that AI could interpret to answer the question. And then also to take what the generators were generating and actually translate that into natural language. So it could kind of put a voice on the AI. We did really well going from natural language to neurosymbolic representation. It was a little bit trickier going the other way because of semantic variations that could result in many different questions for a given output from the GAN. But in terms of this architecture, what we did was is kind of interesting because we focused on a few things. How well does it do at just translating question to question, just an autoencoder? How well does it do at translating a question to what we call a program? And these were the early workings of what we're now doing with the LLMs, where a true program, right, would allow us to generate Python code that could be executed. So we put in the hooks for that early in this work, and then program to question the neurosymbolic representation to a natural language question. And the interesting thing about this work is that the architectures use shared word embeddings, and they use shared word positional embeddings across the networks. And this work was based on some of the early work coming out from Tannenbaum, who was doing a lot of work with neurosymbolic stuff for trying to interpret what you see in images using natural language. And so we used 19 different question types. We performed a 90-10 split for training and tests, and we used over 250,000 training samples. The nice thing about this was we actually could make use of this clever data set that was out there as a benchmark data set, and it had questions that we could use. And then we did basically we did fine tuning on our own data set to kind of stretch it even further. And we had 12,500 test samples. We used a BLUE metric to score this, and BLUE is a bilingual evaluation understudy metric. It's basically just used to study machine translated text. And you can think of it in terms of like it's measuring precision, and it's looking at how well did we do at generating the words or terms that were expected based on the ground truth. So like I said, we did a really good job at being able to translate questions to programs, almost 100% in terms of the BLUE score. And the same is true for question to question. That was expected. Program to question, that's where there's often challenge, and we're still working on that. and there's, by the way, for the TIP-GAN and for the neurosymbolic work, there's papers out there for this. So we actually hooked both of these up together. So we had the neurosymbolic, we set up a 2,000 question experiment, and we had the neurosymbolic translate the questions into representations that then the TIP-GAN could interpret and then use to basically run against the trained model to answer the questions. And we measured how well did we do at the translation and how well did we do at actually predicting whether the initial conditions that were actually translated from the natural language, how well did the TIP-GAN do at predicting whether the model would tip or not? And we did really well in both of these cases. And to be fair, these questions were limited in terms of what we could ask, because we trained the GAN to be all about, will the AMOC tip or not? So the questions had to align somewhat with that kind of setup. So you could ask questions pertaining to values for different variables that are in the model, but it always had to relate to, will this result in the AMOC tipping or not? It was a nice proof of concept. And the one thing that came out of this setup was, what kind of speed up are we going to get out of this compared to a scientist trying to perform the same kind of methodology? So that was really what we were trying to get at with this study was, you know, if I'm a scientist and I have an interesting research question, I've got to translate that question into some workable code. I've got to run the model, in this case, the box model, and then I've got to get the answer and then interpret the result. So you can see that, and this is maybe obvious in some ways, once you have a trained AI method, because we have the translation and the TIP-GAN in there together, we can answer questions so, I mean, amazingly quick, right? And if you can get that kind of fidelity in terms of the skill, it's not comparable to how long it would take for a scientist to do it. Now, again, this is focused on those kind of simple questions. And when you, and we all know that the kinds of questions as an oceanographer that I might ask are going to be much more semantically challenging to answer from this simple setup. And this is where our work is today, trying to overcome some of those sorts of limitations. So what we're doing now is we're focusing on this cascade question and also the generalizability question. So we checked the box. We were able to build this AI simulator to assist with AI climate tipping point modeling. We built an AI assistant. And we did all of this with the AMOC, but now can we generalize this to other types of tipping points? And can we build it further so that we can ask more interesting scientific questions, and so that we can perform things like cascades and ask questions around things like mitigation, or how do we avoid a tipping point? What kind of intervention might help us? You know, so we looked at, and we actually, from that work, we developed something called a 6-box model that involved the overturning for both the Atlantic and the Pacific. So we're now looking, instead of just the Atlantic, we're looking at the Pacific too for the overturning. And we're now looking at coral reef dying, Antarctic and Arctic ice reaching melting thresholds, and then flooding and sea level rise. Technically, that flooding and sea level rise isn't a identified IPCC tipping point. It's more of a regional tipping point that NOAA identifies. But it's very interesting to us to study that, because we want to understand how tipping points in one system affect other systems. So we want to understand climate tipping points and their effects on social tipping points. So flooding is a good example of something that's going to have some social implication that we can actually study. And so that's the point of having that one there too. So we're building reduced models for these. And the question always comes up, how does this relate back to the large GCMs? And, you know, if you're studying in this reduced space, does it really matter? And we've done some studies in terms of representing the dynamics. And we've done a great job at being able to calibrate these reduced models to the large GCMs. We've done it with GISS. We've also done it with CSM. And so we're trying to now build translation models between these reduced models and full models. And I think that has a lot of value because we can find things in the reduced space. And if we can represent the dynamics well in the reduced space, then the question is, can that translate to the larger space? And so we have this new reduced model for 6 boxes for the MOC. Very interesting study there. And we have a journal paper on that work. And we're about to publish a paper on this new coral model that we've built. So the coral model, we built this reduced model from papers and equations that are defined in the papers. This will be the first of these models, the coral. And we're currently working on the reduced models for ice, for the Arctic and Antarctic right now. And what's interesting about the TIP-GAN now is we no longer are building our TIP-GAN to just look for a condition where we're in an on or off state. Now we actually are building the TIP-GAN to understand different states and how we transition between states. So here we're trying to ask the question, are we in a deep circulation pattern for the Atlantic or the Pacific? Or are we in an intermediate pattern for the Atlantic or Pacific? Or are we in this like surface circulation where we are actually going to find shutoffs? And the reason why this is very relevant is because when, getting back to those questions, right? As a physical scientist, when I want to pose an experiment to this system, now we have this rich way of understanding the state of the MOC. We can actually understand when the GAN is imagining initial conditions that are just physically like unrealistic. And also when it's finding states that we weren't aware of before. We show that in this model. Actually, this is a T-SNE embedding. We actually build these T-SNE embeddings from the penultimate layer of the GAN, so we can get, and then we label it with the states. And so you can see in some cases we have these other states. That means it was a state that we didn't necessarily account for in that 6-box model. So we're trying to go down this path of using TIP-GAN to make some discovery. And that's really exciting and also enabling in terms of those questions that one would want to ask of it. And we have this TIP-GAN now built for the coral model too. And we've actually started to look at building some aspect of causality into this. We call that TIP-Cause. It's now trying to predict when tipping points will occur and identify what are the strongest drivers of those tipping points. So your TIP-GAN is living in parameter space, and your TIP-Cause is actually working in state space now. And that's really interesting because we couldn't get at those time step changes that are occurring in our variables. And in order for us to do things like avoid a tipping point, we had to work in that space. And that's really what we're after with this TIP-Cause model. And so we're using a temporal convolutional neural network with attention for this. And we've been applying this model to the 4-box AMOC model to learn causal effects. So attention is actually, well, what's enabling, the transformer architecture and attention are what's enabling what you're seeing today with things like open ChatGPT and all of that, right? The attention is really, really where the importance is. And it's just going to focus on those different subsets of input, and it's going to learn what to attend, the model's learning what to attend to, right? Based on the input of the data and based on what's been learned so far. And in this work, causality is represented by a statistical structural equation modeling method. So it's just basically a model that hypothesizes the relationship among the variables. And it does use this validation step, which is based on a conditional Granger causality. But in the world of causal inference, right, So yeah, there's lots of debate around causality in machine learning right now. But I would say that we're getting like a kind of a weak causal relationship understanding from this model. So we used 8,000 total model runs from the 4-box model that we generated. We trained over 6,000 and we tested over 2,000. We had a balance between AMOC collapse and AMOC non-collapse cases. And what you're seeing in this plot here on the right is the dotted line is the ground truth about that forecast. And then the solid line is our prediction. So it's doing an excellent job of predicting pretty much all of the variables. Now, one thing to keep in mind here is, and this is what we're currently overcoming, is that it's using all of the other time series to predict a particular variable. So it's using the full time series of the other variables to predict one of these variables. So for example, the AMOC overturning is being predicted based on the other time series. And what we are doing now is forcing it to only use historical information from those other variables in order to do that long-term forecast, which is more like a standard forecast, right? And so in this case, it identified temperature and salinity in the north boxes as having some kind of causal effect on the outcome of the overturning. And so we set up an experiment to just evaluate the validity of this. And what we did was we took, we separated our shutoffs from our non-shutoff cases. We took the values from our non-shutoff cases and we replaced the values for just those two variables. In this case, just salinity in the shutoff case to see if we could move that trend from being a shutoff to being closer to being a non-shutoff. And we get you see in that green line, we get like, we get a bump there in terms of moving it. And we did the same with temperature and we see that a bump gets a little bit higher, closer to a non-shutoff case. And then when we include both of them, we move it all the way to an example. It looks very much like a non-shutoff example. And so those are some of the early results coming out of our causality work, which I think they're actually very interesting results and promising for what we're going to do in the future with this model. I will also say that, in all fairness, this was also a non-stochastic version of the model too. The stochastic version, the results are very similar to this, but just wanted to be clear on that. Okay. So I want to make sure I'm not out of time here. Yeah, good. So I'm going to tell you about what we've been doing with LLMs to advance this TIP assist work. We're trying to move from the simple question answering to fully automated AI assistant. Our goal is out there. We want a physical scientist to be able to pose a scientific experiment, and we can decompose that experiment and run all the parts that we need to run all the parts of our system that we need to run, bring all the results together and formulate some kind of result to give back to our physical scientists, whether it be plots, whether it be a full paper or abstract. That's ultimately our goal. It's a very challenging thing to do, as we're seeing. What we did in this case was we just wanted to understand, because things like the models like ChatGPT, they're not trained on scientific literature. They're trained on basically all of the things you can find on the internet, minus like the journal papers and things that necessarily aren't open. And so if we want to be able to answer scientific questions about the AMOC, we have to train the model to talk the same to understand the science, like using the same kind of lexicon. And so so we asked the question, if we fine tune a model on scientific literature, will it do a better job at answering questions than a non-fine tuned model? So we can fine tune Llama. And at the time, this was a couple months ago, we did this. We fine tuned Llama. This is before Llama 3 came out. And what we did, and let me tell you, it's very challenging to fine tune. It's very challenging to generate the training data that you need to fine tune. And so what we did was we had oceanographers on our team compose a set of, so gather a set of papers to generate a collection of them. They did a small set and they extracted from those papers questions and answers and the context, like a section of the paper where the answer could be found. And they did, in some ways, they tried to normalize this by only using authors that were producing content that was similar in terms of the AMOC. We used something interesting because in order to do this, it takes a lot of time. And so you can't do too many of these, but to fine tune, you need a minimum of about 1,000 samples and maybe more given the vocabulary size. So what we did was we used ChatGPT actually to create semantic variations of the questions and answers to basically increase the size of our training data set. And that turned out to work well for us. So we were able to create a training data set to fine tune and then a test data set, pretty small. It was a very limited experiment, by the way. Some interesting things that we found from this work is that, and we had 5 authors and a set of questions from each. The interesting thing we found, which is probably not at all surprising to you by now, is that in terms of the base model, llama model, and our fine-tuned llama model, the answers tend to be very chatty in terms of the number of words that it's going to return versus your ground truth. And also noisy, that's for sure. But we did see when we used a RUG-1 scoring, and arguably maybe RUG-1 isn't the best score to use. We're changing that now. But because RUG-1 is looking at how many of the words that returned in the answer overlap with those set of words that were in the ground truth or expected answer. So, you know, it's in some ways, it's not going to always be fair because you can answer a question and it could just be, it could be semantically different, but yet be a correct answer. So, so we're working with semantic similarity measures now to overcome that problem. But we did see with both with the Rouge and Blue scores that we were getting a little bit of a bump in terms of performance if we used our fine-tuned model to answer the questions. So our new experiments, actually, there were some flaws with this first study. One, sometimes the answers weren't always standard that the oceanographers gave us, and there was a mix of true, false, or short answer. And so we really wanted to be very constrained in terms of what we were allowing with respect to the answers and the questions. So we standardized things much more. We built a larger data set. We created more semantic variations. And we actually had a team of 3 oceanographers that were, each one was assigned a set of questions and answers that they were generating, and then it was graded by the full team. And so in some cases, if there wasn't full agreement across the team, we just didn't include it, right? In some cases, you wouldn't see full agreement. So we started with 299 examples, and we created 20 variations per example. So that really bumped us up quite a bit in terms of training set size. What's interesting is that Llama 3 came along. And so we had to ask the question, because Llama 3 is actually very good. We had to ask the question, how much different is Llama 3 from GPT-4 and Llama 2? Because we were using Llama 2. And it turns out that, you know, Llama 3 is actually, even Llama 2 wasn't too bad. I mean, when you look at this in terms of these RUG-1 scores, again, semantic variations are going to cause these scores to be lower. So so the trend sits kind of lower in terms of this distribution. But in terms of like scoring, comparing the 3 to each other, you know, it's surprisingly that the llama is not doing too much worse than the GPT-4. In some cases, does better. We did actually look at comparing these three using the SBERT score, which is looking at semantic similarity using large language models. I don't know, maybe somewhat of a cat chicken and egg problem here, but anyway, we did actually use the semantic similarity approach to this, and you can see that, okay, now when you allow for more semantic variation, all of the scores tend to be higher. But you still see this, that llama is actually quite competitive with GPT-4. That's interesting and good to see. That was on the short answers. On the true false questions, we actually see GPT-4 and Llama 3 do really, they do really well. They compare well to each other. Llama 2, not so much. And then we did the fine-tuned model. We had to heuristically clean the output of the fine-tuned model. We fine-tuned Llama 3. And the problem with the output when we do the fine-tuning is we often get multiple responses. So it'll say false, and then it'll give some short answer. Then it might say false again, and another short answer. It does that. So our heuristic is that we basically take the first answer we find, and that's our answer, and that's what we use to grade it. We did see a slight bump in our fine-tuned version of this. True false was a little lower, actually. We're still tweaking this model. We're actually running experiments where we don't include context in terms of the test set that we held out. We also are tweaking, increasing our semantic variations even more. Because interestingly enough, we did see that when we looked at measuring how the SBERT score in terms of the number of variations we're creating, we actually, as we increase the number of variations, we're still seeing the score improving, which means we didn't hit that wall yet where, you know, you're just not varying it much more. There are enough variations that we see some change in score. This is actually, I was really happy to see this, because I always questioned whether semantic variation was just going to produce a lot of duplicates, which doesn't help machine learning much. And it doesn't appear that that's happening. All right, I'm almost at the end of this talk. So everybody, thanks for hanging in there. I know it's a lot. And so the question is, can we engage these different tools based on a question? And this is really the heart of what we're trying to get at with this TIP assist. Like, okay, can we use LangChain? Can we give it a complicated question or experiment, and it knows how to decompose it, call in all the parts of our AI system, answer the question by answering the different parts, and then return some kind of response? The first step in doing this is just seeing the behavior of LangChain, trying to actually understand how it executes our code. So we started with just trying to have it execute our box models that are written in Python. So it's generating Python code, running it, actually producing plots, and producing abstracts of what the results are telling it. It does all of that. We use 1,600 questions, 800 specific to the 4-box, 800 specific to the 6-box. And we're just trying to see how well does it do at answering the question. We can't measure how well does it do at calling the right tool, because it really makes those internal decisions on its own. And sometimes it doesn't do it right. Sometimes it calls on the 4-box model and then realizes, oh, I can't answer this question using the 4-box model. I'm going to try the 6-box model instead. And sometimes it just uses the 6-box model. And I think that's okay. Because, you know, for the 4-box model, it's getting the answers correct in terms of the outcome of the AMOC collapsing or not, 94% of the time, and 70% of the time for the 6-box. 6-box arguably more complicated. And these are what some of the questions look like. So sometimes we're going to ask a question about a variable that doesn't even exist in the 4-box model. And so we're presuming it should always use the 6-box model, but it actually sometimes it will try the 4-box model. And so those are interesting questions that we're trying to understand. And what's interesting about using this is we can get some kind of thought process out of it as to why it's choosing to use a tool versus not, and why it's doing it, what does it need to do. All of this is kind of pretty standard with LangChain. The challenges with this work is having it know what to engage in given a complicated question, breaking it up into parts, and having it know what of our code to engage to try to answer those parts. That's our current big problem we're working on right now. All right, so thank you for hanging in there. I've shared some of our early work related to what we've done with respect to TIP-GAN and what it can learn in terms of bifurcations. I've shared what we've been doing with neurosymbolic translation and how we're now moving into this LLM space. Some early results regarding causality and the promise of kind of using this methodology, not only to give you like a big speed up, but hopefully what you're seeing is that the AI is able, the TIP-GAN is able to find those places in that large parameter space where you have tipping points. So your model runs can be very directed to those spaces, which in some cases you may not even have been aware of. And I think that's where there's a big win on the TIP-GAN. And then I think these attention-based architectures hold a lot of promise for understanding things like causality and helping us with trying to avoid these tipping points. And it does look like so far we are getting some nice generalizability out of our methods. And we're currently now building this TIP-GAN to do cascades. So the TIP-GAN's objective is actually going to be, couple these models and then try to cause a cascade to occur. And I think that's something interesting. I also mentioned that we're working on this idea of trying to map or build a translation from reduced models to full models, and then seeing how well what we learn in the reduced space can be applied to the full space. We're working towards this concept of a digital twin. We think climate tipping points could be a great addition to the digital twin that is part of ESTO. And we're also working on connecting this with things like remote sensing and bringing in observational data. Okay, I think that's the end there. Yeah.
So thank you so much. So we definitely have a few minutes, go a few minutes over for questions. I know we have one question in the chat, which I'll pull up. Are there other questions in the right now? Okay. So I'm not sure if you can see this in the chat, Jennifer, but I believe this is Michael Wright, and he asked, given the complexity of these learning models, is it true that they take into account the log in response to, say, reduced emissions or reduced solar incidents?
Hold on, I need to increase the volume here. I'm not able to hear you.
I can also increase our microphone.
Okay, yeah, I just increased mine so I could actually hear. I'm sorry, if you could repeat that, I just couldn't hear it.
Yeah, no worries. This is also in the chat, which you might be able to pull up, but if not, the question is, given the complexity of these learning models, is it true that they take into account the lag in response to, say, reduced emissions or reduced solar incidents?
In terms of, so could you elaborate on what you're getting at with that question?
It's in the chat. If whoever put that in the chat, if you want to
let me stop
unmute yourself.
So I can, yeah, let me stop this so I can get into the chat here.
Yeah, you're welcome to unmute yourself and clarify or elaborate on the question.
I'm not sure if everyone can see the chat, Maggie. I see a box, but I don't see anything, any text in it.
Okay, I'm just asking the person that asked the question, which is M. Wright, which I think is Mike.
Yeah, so M. Wright, I'm just curious, when you say lag in response, what are you, could you clarify that so I can understand that better?
I see they're still online. Maybe they've stepped away from their computer. In the meantime, do we have other questions here?
Yeah, Jennifer, I was wondering if you all see LangChain and ChatGPT, or GPT-4 rather, as a replacement for fine-tuning the llama models, and sort of like how you're managing those two things.
Yeah, it's a good question. I mean, we were in one way, we're pleasantly surprised to see the performance without fine tuning. In another way, I think we haven't measured this as well as we could to get at, is it really understanding how to answer the scientific question, or you know, so I think there's more to that in terms of measuring it, but I do think that for us, right, Llama, we do want to use Llama instead of ChatGPT just because of some of our personal restrictions, but it was nice to see that Llama's comparative in performance. That was actually a surprise.
Yeah. And then for that true false score, is success for that 100%? Like it's always answering that accurately, or how do you guys measure that?
Yeah, it has
Okay.
to be.
Right.
So.
Okay, so that online question, I realized it went just privately to me, so I re-put it in the chat. They're working on unmuting, but in the meantime, we have another question in the chat. This is from Sonia. And she said, when you mentioned the fine-tuning llama, did you use LORA or other quantization techniques to reduce computation intensiveness?
Yeah, we did use Laura. We did use Laura. And that's probably about most of the detail I can give you about it because it was done by one of my colleagues. But yeah. I will tell you that, you know, fine tuning is definitely a challenge if you want to go down that path, not only in terms of the computation and resources that are required to do it, but also that building that data set, because like I said, I think even right now, you know, the number of samples that we have, we're still not seeing loss plots that I would say are like great. They tend to be more overfit. And so we're gonna try to increase the size of that sample. We're gonna try to double it. And I think really when you start getting into these fine-tuning problems, you're gonna have to have a sufficiently sized data set. And now I think RAG could be used to help with overcoming some of the challenges with building the training data sets, but I think there's challenges there too. So
Okay. I actually have a question. So when you were kind of going through the motivation for the project, you were discussing, in addition to identifying tipping points and cascades, the possible applications to mitigation and adaptation. So I know you're right now focusing more on developing the cascade side of it, but are you guys thinking about or trying to move into creating kind of a tip assist, but instead of scientists asking questions, more aimed at stakeholders that would want information about mitigation or adaptation?
yeah, we are moving towards that, actually. We're working towards a way to evaluate different intervention methods. And that's particularly something that we can do with coral. That's a big one, right? Because there are interventions like that. And let me just say, not in terms of like saving coral, but in terms of the effect of coral dying. So when you get coral die off, what you have is an effect on wave attenuation. And so when you couple that with a sea level rise, then your coastlines are more likely to be flooded. And so we can explore intervention methods in terms of stopping those flooding incidents. And so that's a good use case for it. Obviously there are other types of interventions that are of interest, like cloud seeding, but I think those, you know, are something that we may be, those are maybe harder for us to model at this point.
Is it?
Yeah, they'll just be
The mics, okay. Hi, thank you for the presentation. I just noticed on the last slide, there was the mention of, because the results were so promising with generalizing, the model, is there, are you guys moving, I think it said something about moving towards other systems other than climate. What would some of the systems that this work has applications to be other than climate?
Yeah, that's a good question, because this comes up in the academies of science, that they talk about tipping points in terms of different systems, right? Which is what triggered us to start looking at things like flooding. But yeah, social tipping points, economic tipping points, those are all systems that we could explore. But I think you can you could set this up in a way, you know, as long as you fully define and model what your tipping points are. At this point, I don't think there's much stopping it from being adaptable to different systems. Just, it's pretty generalizable the way that we've built it. You have to replace the model. You have to replace the scientific literature if you're doing the fine tuning and the kind of questions that you can support. But other than that, like the TIP-GAN and the causality and the tip assist, those are pretty, they're not specific to any of these tipping points, so.
Awesome. Thank you.
Okay, I think we'll just try to wrap up with, we do have a clarification to the question that was asked earlier, which is in the chat now. I don't know if you see that, Jennifer, or if you want me to read it.
No, I do see it. Yeah, thank you for clarifying. Yeah, it does. I mean, we do, like in some of these reduced models, we do have some variables representing some of the atmospheric changes, but they are forecast models, right? I think when you want to start looking into things that might be more actionable, that's when I think, you know, observations might be more interesting to include. And that is something that we're working on that actually also. So let's see. Yeah, so it doesn't specifically, when you specify the initial conditions, it doesn't specifically take into account some of these things, but it could. It just doesn't right now.
Okay, I think we'll wrap it up there. So can we give another round of applause? Thanks.
Yeah. Thank you again.
And even though you couldn't come in person, we're very happy to see you virtually. Yeah, let us know if you do come up to visit.
Yeah, sounds good. Thank you all.
Thanks, Jennifer.
Thank you.
Thank you.